Right now, somewhere in the Milky Way, a star that has been burning for millions of years is about to just disappear. No explosion, no supernova, no fireworks. It will simply collapse in on itself and vanish from the universe, leaving behind something so dense, so gravitationally extreme that not even light can escape it. And here is the wild part. We actually watched this happen. For the first time in history, astronomers caught a star in the act of silently becoming a black hole. And that is just one type of black hole. Because as it turns out, these cosmic monsters come in very different flavors. From ones forged in the death throes of giant stars, to ones born in the first fraction of a second after the Big Bang itself, to ones sitting right at the center of our galaxy that might not even be a black hole at all. So today, we are going to break down every single type of black hole that scientists have discovered, theorized, and in some cases, just detected for the very first time. And I promise you, by the end of this, the way you think about the universe is going to be fundamentally different. Let us start at the beginning, because the story of black holes is honestly one of the strangest chapters in all of science. The idea that something could have gravity so strong that light itself could not escape goes all the way back to 1783, when a British thinker named John Michell wrote a letter describing what he called a dark star. But the real math did not show up until 1915, when Albert Einstein published his general theory of relativity. And here is where it gets beautifully ironic. Just months later, a German physicist named Karl Schwarzschild, who was literally serving on the Russian front during World War I, solved Einstein's equations and found something disturbing hidden inside them. There was a critical radius around any mass where, if you compressed matter small enough, gravity would become so overwhelming that nothing could ever leave. Einstein received Schwarzschild's letter from the trenches, and you know what his reaction was. He thought it was mathematically interesting, but physically impossible. Einstein, the man whose own theory predicted black holes, spent the next 2 decades arguing they could never actually form. Arthur Eddington, one of the most brilliant astrophysicists of the early 20th century, famously declared, "There should be a law of nature to prevent a star from behaving in this absurd way." Well, the universe did not care about their opinions. The first type of black hole we need to talk about is the one that forms when massive stars die, and these are called stellar mass black holes. They are the most common type, and they are everywhere. Astronomers estimate our Milky Way galaxy alone contains somewhere between 10 million and 1 billion of them. Let that sink in. Up to 1 billion black holes just in our galaxy. Here is how they form. A star that is at least about 8 to 10 times the mass of our Sun spends millions of years fusing hydrogen into helium in its core, and that fusion creates outward pressure that perfectly balances the crushing inward force of gravity. It is a beautiful cosmic tug of war. But eventually, the star runs out of fuel. And when that happens, gravity wins. The core collapses catastrophically, and in many cases, this triggers a supernova, one of the most violent explosions in the universe. What is left behind if the core is massive enough is a black hole. Typically, these range from about 3 to around 100 times the mass of our Sun. The most famous example is Cygnus X1, which holds a very special place in history. It was discovered back in 1964 when a pair of Geiger counters were launched on a rocket from New Mexico and picked up an incredibly powerful X-ray source in the constellation Cygnus. It took almost a decade before astronomers confirmed what it really was. In 1972, 3 scientists working independently, Charles Thomas Bolton, Louise Webster, and Paul Murdin, identified it as the first strong black hole candidate. And even then, the debate raged on. Stephen Hawking famously made a bet with physicist Kip Thorne in 1974 that Cygnus X1 was not actually a black hole. He called it insurance. If black holes did not exist, at least he would win the bet. He conceded in 1990. Today we know Cygnus X1 intimately. It sits about 7,200 light-years from Earth. It has a mass of about 21 times our Sun, and it is locked in a 5.6-day orbit with a blue supergiant companion star, roughly 40 times the Sun's mass. And just this month, in April 2026, researchers published something remarkable in Nature Astronomy. Using 18 years of radio telescope data from a planet-spanning network, they measured the power of Cygnus X1's jets for the first time ever. Those jets are blasting out energy equivalent to 10,000 suns. They literally watched the jets dancing, being bent and pushed by the companion star's wind as the black hole orbited. It is the first time we have measured the instantaneous power of a stellar black hole's jets, and it confirms theories about how black holes shape the space around them. But here is where the story of stellar black holes got turned on its head. In February 2026, a paper published in Science described something that had been hiding in plain sight for over 5 years. A star in the Andromeda Galaxy, 2.5 million light-years away, designated M31-2014-D S1, had been a massive red supergiant, about 13 times the mass of our Sun. In 2014, NASA telescopes noticed it getting brighter in infrared light. It glowed for about 3 years, and then it just faded away, disappeared. No supernova, no explosion, nothing. The lead researcher, Kishalay D. from Columbia University, said something that honestly gave me chills. He said, quote, "It comes as a shock to know that a massive star basically disappeared and died without an explosion, and nobody noticed it for more than 5 years. What happened was a failed supernova. The star's core collapsed, but the shockwave was too weak to blow the outer layers off. Instead, nearly everything fell inward and formed a black hole. The outer layers were gently pushed away as a shell of dust, and the star simply ceased to exist." This was the most detailed observation ever of a star making that transition, and it fundamentally changes our understanding of how stellar black holes are born. We always assumed stars of this mass would explode. Turns out, some of them just go quietly into the dark. Now let us go much, much bigger. Because while stellar mass black holes are impressive, they are tiny compared to the monsters lurking at the centers of galaxies. Supermassive black holes are, without exaggeration, the most extreme objects in the known universe. We are talking about black holes with masses ranging from hundreds of thousands to billions of times the mass of our Sun. And they sit at the hearts of most, if not all, massive galaxies. Our own Milky Way has one. It is called Sagittarius A star, and it weighs in at about 4.3 million solar masses. It sits roughly 26,000 light-years from Earth, and in May 2022, the Event Horizon Telescope gave us the first image of its shadow. But Sagittarius, our star, is actually modest compared to the real titans out there. The black hole at the center of galaxy Messier 87, the one that gave us the very first black hole image back in April 2019, is about 6.5 billion solar masses. Billion, with a B. But here is the thing that keeps astrophysicists up at night. How did these monsters get so big, so fast? Because the James Webb Space Telescope has been finding supermassive black holes existing when the universe was less than 1 billion years old. And our standard models simply cannot explain how they grew that enormous in such a short amount of time. This is what scientists call the too big, too fast problem. And 2026 has been an absolutely wild year for cracking it open. In January, a study published in Nature solved one of Webb's biggest mysteries. You know, those strange little red dots that kept showing up in the telescope's deep field images. Hundreds of them, scattered across the earliest epochs of the universe, glowing red and then vanishing about 1 billion years later. Researchers at the Cosmic Dawn Center in Copenhagen figured out what they are. They are young, supermassive black holes wrapped in dense cocoons of ionized gas. And here is the kicker. They are about 100 times less massive than previous estimates suggested, with masses between 100,000 and 10 million times the Sun. Professor Darach Watson, one of the lead researchers, explained that these are baby supermassive black holes caught in the middle of their growth spurt, gorging on the gas surrounding them. The heat generated by this feeding frenzy shines through the cocoon and creates that distinctive red glow. This finding, published on the front page of Nature, tells us we are watching the origin story of supermassive black holes in real time. And if you thought that was mind-bending, also in January 2026, a team from Waseda University found a quasar at a distance of about 12 billion years in the past that was feeding at 13 times the Eddington limit. That is 13 times the theoretical speed limit for how fast a black hole can consume matter. At this rate, radiation pressure from the infalling material should push everything away and stop the feeding. But this black hole was not only gorging beyond its limit, it was simultaneously blasting out powerful X-ray emissions and launching a radio jet. According to most models, those three things should not be happening at the same time. It suggests we are catching a black hole during a brief, unstable, transitional growth spurt that our current physics cannot fully explain. And then, just this April, a supermassive black hole in a galaxy called J1007+3540 woke up after being dormant for nearly 100 million years and erupted like a cosmic volcano. Fresh jets blasted outward, creating distorted structures stretching nearly 1 million light-years across. Meanwhile, in galaxy V-Val 340a, astronomers found the largest stream of superheated gas ever observed flowing from a galaxy, stretching 20,000 light-years from the center, driven by a precessing, wobbling black hole jet shaped like a giant S. The universe's supermassive black holes are not just sitting there. They are alive, active, and reshaping entire galaxies. All right, now we enter the realm of the mysterious. Because between stellar mass black holes, which top out around 100 solar masses, and supermassive black holes, which start at hundreds of thousands, there is a gap, a huge, puzzling gap. And this is where intermediate mass black holes live, or where they should live. Because finding them has been one of the biggest challenges in modern astrophysics. Intermediate mass black holes range from roughly 100 to 100,000 solar masses. They are the missing link. If supermassive black holes grew from smaller ones over billions of years through mergers, then intermediate mass black holes should exist as a transitional phase. The problem is, there is no common natural process that easily makes a black hole of this size. Stars do not get big enough to collapse directly into one, and merging enough stellar mass black holes takes an incredibly long time. But we are finally finding them. The strongest candidate sits in Omega Centauri, the largest and brightest globular cluster visible from Earth. Using over 500 Hubble images spanning 20 years and cataloguing the motions of 1.4 million stars, astronomers discovered 7 stars in the cluster's core that should not be there. They are moving so fast, they should have escaped the cluster entirely. The best explanation is an intermediate mass black hole of at least 8,200 solar masses pulling them in. It sits just 17,700 light-years from Earth, actually closer to us than Sagittarius A star. And then came the gravitational wave bombshell. In November 2023, LIGO detected a signal designated GW231123, and when they analyzed it, the results were staggering. 2 black holes, roughly 100 and 140 times the mass of the Sun, had smashed together to create a monster of 225 solar masses. This is the most massive black hole merger ever detected. But what made it truly extraordinary is that both of those original black holes fall in or near what physicists call the forbidden mass range, between about 60 and 130 solar masses, a process called pair instability. Supernova should completely destroy a star, leaving no remnant at all. No black hole, nothing. These black holes should not exist, unless they were not born from stars at all, but were themselves products of earlier mergers. Black holes merging with black holes, growing step by step, hierarchical mergers. And these two were spinning near the maximum rate allowed by Einstein's theory of relativity, about 4 million times the rotation rate of Earth. We are watching black holes evolve, generation by generation, like a cosmic family tree. Now for the type that could change everything. The one that, if confirmed, would rewrite textbooks and solve one of the biggest mysteries in all of cosmology. I am talking about primordial black holes. Every other type of black hole we have discussed forms from stuff that already exists in the universe. Stars, gas clouds, mergers. But primordial black holes are different. They would have formed in the first fraction of a second after the Big Bang itself, born from density fluctuations in the incredibly hot, dense soup of the infant universe. No star required. The idea was first proposed by Soviet scientists Yakov Zeldovich and Igor Novikov in the 1960s, and Stephen Hawking further developed it in the 1970s. But for decades, primordial black holes remained purely theoretical, until possibly now. On November 12, 2025, LIGO detected a gravitational wave signal catalogued as S251112CM. And when researchers analyzed it, they found something that stopped them cold. The collision involved at least one object with a mass less than that of our Sun. Let me explain why that is such a big deal. The minimum mass for a black hole formed from a dying star is about 1.4 solar masses. That is a hard physical limit. No known stellar process can create a black hole lighter than that. But this signal showed an object between 10 and 87% of the Sun's mass. Too heavy to be anything normal, too light to be a stellar black hole. Two researchers at the University of Miami, Associate Professor Nico Cappelluti and PhD student Alberto Magaraggia, built a framework to explain what LIGO might have found. Their conclusion, published in early 2026 and headed for the Astrophysical Journal, is that the most plausible explanation is a primordial black hole born in the earliest moments of cosmic history. They estimated how many primordial black holes LIGO should be able to detect and found that the rarity of this signal is actually exactly what you would expect. It is rare because primordial black holes themselves should be rare. And here is the part that could reshape our entire understanding of the cosmos. If primordial black holes exist in sufficient numbers, they could account for a significant portion or even all of dark matter. Dark matter makes up about 85% of all matter in the universe. We know it is there because of its gravitational effects, but we have never directly detected it. If dark matter is not some exotic undiscovered particle, but rather billions of tiny black holes forged in the first fraction of a second after the Big Bang, that changes everything. Now, I need to be honest with you. This is not confirmed yet. Some scientists think the signal could be noise in LIGO's detectors, and there is an alternative interpretation involving a subsolar mass neutron star merger. Cappelluti himself has said they will need to detect another such signal, or even several, for smoking gun confirmation. But the tools are improving rapidly, and the math fits. We might be standing at the edge of one of the most profound discoveries in the history of astrophysics. There is one more type we need to talk about, and it is both the newest and possibly the most important for understanding how the universe built itself. These are called direct collapse black holes. Remember the too big, too fast problem? How supermassive black holes appeared when the universe was less than 1 billion years old. Well, there are two competing theories. The light seed theory says you start small, with stellar mass black holes, and grow through mergers over billions of years. But that takes too long to explain what Webb is seeing. The heavy seed theory, the one behind direct collapse black holes, says something much more dramatic happened. In the very early universe, under specific primordial conditions, pristine clouds of gas did not fragment into stars. Instead, they collapsed wholesale, directly into black holes of 100,000 to 1 million solar masses. You skip the star phase entirely. You just go straight from a gas cloud to a massive black hole. In 2025, the James Webb Space Telescope found what might be exactly this. In a system nicknamed the Infinity Galaxy, where two spiral galaxies are colliding, Webb detected a 1 million solar mass black hole embedded in ionized gas between the two galaxy nuclei. And the system also has two additional active supermassive black holes in each galaxy's core, making it a triple black hole system. Peter van Dokkum from Yale, who led the study, was careful to note they cannot say definitively they found a direct collapse black hole. But the data strengthens the case while eliminating competing explanations. And I saved the most mind-bending twist for last. What if the object at the center of our galaxy, the thing we have been calling Sagittarius a star for decades, the object Reinhard Genzel and Andrea Ghez won a Nobel Prize for identifying, what if it is not actually a black hole? In February 2026, a team led by Valentina Crespi at the Institute of Astrophysics La Plata in Argentina published a study in the monthly notices of the Royal Astronomical Society proposing something radical. They suggest that Sagittarius A star could instead be an ultra-compact core of dark matter made of particles called fermions. And before you dismiss this, listen to what their model can do. It reproduces the orbits of the S stars, those stars that whip around the galactic center at speeds up to 30,000 kilometers per second, roughly 10% the speed of light. It matches the orbits of the dust-shrouded G-sources near the center. It is consistent with the famous shadow image captured by the Event Horizon Telescope. And when combined with the latest data from the European Space Agency's Gaia mission, it explains the Milky Way's rotation curve at vast distances. Their co-author Carlos Argüelles put it beautifully. He said, "We are not just replacing the black hole with a dark object. We are proposing that the supermassive central object and the galaxy's dark matter halo are two manifestations of the same continuous substance." Now, the researchers themselves are the first to say this is not necessarily more probable than the black hole explanation. The EHT's founding director, Shep Doeleman at Harvard, has pointed out that observed magnetic field patterns near the event horizon are particularly consistent with black hole properties. And fermionic dark matter cores have a theoretical mass limit of about 10 million solar masses, which does not explain how you would get a 6.5 billion solar mass object like M87 star. We need better data. But the fact that we cannot currently distinguish between these two scenarios at the center of our own galaxy, that is humbling. So let us step back and take in the full picture. We live in a universe where dying stars silently collapse into black holes without even a whisper, where monsters millions and billions of times the mass of our sun anchor entire galaxies and reshape them with jets spanning 1 million light-years. Where missing link black holes are being assembled through cosmic collisions, generation after generation. Where objects born in the first heartbeat of the Big Bang might be lurking invisibly all around us, possibly making up most of the matter in the cosmos. Where gas clouds may have skipped straight to becoming black holes without bothering with stars first. And where the very definition of what sits at the center of our galaxy is still up for debate. We went from Albert Einstein insisting black holes were impossible to Carl Schwarzschild solving the math from a World War I battlefield, to Stephen Hawking making bets about whether they were real, to literally photographing one, all in about a century. And now, in 2026, we are watching stars collapse into them live, detecting their primordial cousins for the first time, and questioning whether the most famous one of all might be something even stranger than we imagined. The universe is not just stranger than we suppose. It is stranger than we can suppose. And the story of black holes is nowhere close to being finished. If this video blew your mind even a fraction as much as researching it blew mine, hit subscribe because we cover discoveries like this every single week. Drop a comment telling me which type of black hole fascinates you the most. Is it the silent stellar collapses? The primordial ones that could explain dark matter? Or is it the possibility that Sagittarius A star might not be a black hole at all? I genuinely want to know. And if you have a friend who loves space, send them this video. I guarantee it will start a conversation.